In this video, you will be learning all about function notation. You will be able to use function notation when substituting for x and y. You will be able to use the graph to determine values of function, and you'll be able to solve when two functions are equal to each other. So recall that in a function, for every value of x, there is only one value of y. So then every time we plug in an x value into a function, we will get only one y value. Now let's look at the example y equals 2x plus 1. Now, is this a function? Well, yes it is. Y equals 2x plus 1 is a linear relation. All linear relations, unless it has a slope that is undefined, are functions. Now this in fact has a slope, it doesn't have an undefined slope, so this is in fact a function. Now let's think of a function as a machine. When you input an x value into this function machine, it will produce a y value, which is your output. So in our example, the machine that we're talking about here is 2x plus 1. Now every time we put in an x value, we input an x value into this machine, we will get one y value. So for example, if we input 3 into this function, 2 times 3 plus 1 is 7. And if we input negative 2 into this function, 2 times negative 2 plus 1 is negative 3. So when our input in this function is 3, the only output we get is 7. And when we input negative 2, the only output we get is negative 3. Now when we know a relation is a function, we can use something called function notation, and that is this symbol right here. Instead of using y, we can write this little symbol, which is f open bracket x close bracket. This is pronounced as f at x. F just represents the function, and f at x means that y is a function of x or y depends on x. So every time we have a function, we can always just replace y with f of x. Looking back at our example, y equals 2x plus 1, this was in fact a function, so we can rewrite in function notation f at x equals 2x plus 1. Now remember, this is the same thing as y equals 2x plus 1. So our function is f at x equals 2x plus 1. When using function notation, when we want to find out what the function is equal to when x is equal to 3, all we really do is replace x with 3 every time we have an x. So instead of f at x, we will have f at 3 is equal to 2 times 3 plus 1. So f at 3 is equal to 7. So when we input a 3 into the function, we will get 7. Therefore, the point 3, 7 is on this relation. Now in this example, f at x is equal to negative 3x plus 1. Now we want to determine f of 4 and f at negative 2. This is really asking what is the function, and I'm going to use f to show the function. So what is the function when x is equal to 4, and what is the function, or what is the y value, this is the same thing, when x is equal to negative 2. Now remember, these are the exact same thing, the function and our y values here. To solve this, we start off by writing our original function. F at x is equal to negative 3x plus 1. Now whenever we see the x, we're going to replace that with 4. So f at 4 is equal to negative 3 times 4 plus 1. So f at 4 is equal to negative 11. And again, we're going to start with our original function. So f at x is equal to negative 3x plus 1. We're going to replace our x value with negative 2. So we're finding out what f at negative 2 is. That's equal to negative 3 times negative 2 plus 1. So f at negative 2 is equal to 7. Sometimes another letter is used to represent a function. It's not always f. In example 2, we're using h to represent this function. So the function is h at x equals 3x minus 2. And in part A, we're trying to find the function h at negative 1. So we're starting off with a function h at x is equal to 3x minus 2. We're going to replace that x with negative 1. So h at negative 1 is equal to 3 times negative 1 minus 2. So h at negative 2, or negative 1, is equal to negative 5. In the next one, we're finding h at a. Now this is a little weird because a is not a number, but we can still do the same thing. So our function is h at x equals to 3x minus 2. Now instead of x, we're just going to replace that x with this variable a. So h at a equals 3a minus 2. Now that can't be simplified any further, 3a minus 2, so that is in fact our final answer. H at a is equal to 3a minus 2. Now the next one is h at x plus 5. Now this is a little different from the other ones, but we're trying to find out what the function h is at x plus 5. So again, we're going to start off with our original function. Our function is h at x equals to 3x minus 2. Now instead of just writing x, we're going to write this x plus 5. So we're going to input that x plus 5 in wherever we see x. So h at x plus 5 is equal to 3, and this is going to be times x plus 5 minus 2. Now we are going to have to distribute this. So h at x plus 5, we'll need to distribute that 3 into the brackets. So 3x plus 15 minus 2. And if we simplify that, h at x plus 5 is equal to 3x plus 13. Now in the next question, we're looking at h at 3 minus h at 1. So we can solve this by doing them separately and then subtracting them. So h at 3 is our first function, and then h at 1 is our second function here. So if we start off with our function h at x, that's equal to 3x minus 2, and we're trying to find out what h at 3 is. So 3 times 3 minus 2. So h at 3 is equal to 7. And h at 1, I'm going to skip a step here. So h at 1 is equal to 3 times 1 minus 2. So h at 1 is equal to 1. Now we're looking for h at 3 minus h at 1. So h at 3 minus h at 1 is just 7 minus 1, which is just 6. So the next question seems a lot different. It's negative 2 times h at negative 3. Now we know how to do this part, h at negative 3. So let's go ahead and just start off by doing that. So our function h at x is equal to 3x minus 2. H at negative 3 is equal to 3 times negative 3 minus 2. And that's just equal to negative 11. So we need to find negative 2 times this h at negative 3. So that's negative 2 times, and we're going to replace this h at negative 3 with negative 11. So that's just equal to 22. So in the next question, we're looking for x. When h at x is equal to negative 4. H at x, do you remember what that is? That's just our y value. Y is equal to negative 4. So our function here, h at x, is equal to 3x minus 2. We have h at x this time. We have their y value. That is just negative 4, and we're looking for x. So our unknown variable here is x. We're just solving this equation for x. So it becomes negative 4 plus negative 2 equals to 3x, and that is just negative 2 equal to 3x, and if we divide both sides by 3, x is just equal to negative 2 over 3. In the next example, we're going to be determining our solutions from a graph. So remember our function notation, f at x. X are just our x values, and f at x are just our y values. So f at 2, that means x is 2. We're looking for our y value when x is 2. So f at 2, if we look at the graph, x is right here when it's equal to 2, and our function is equal to 4. So f at 2 is equal to 4. For f at 0, x is just equal to 0, and we're still looking for our y value when x is equal to 0. So on the graph, that would be right here. So our function, f at 2, or f at 0, is equal to 0. Now in part C, we're looking for x when f at x is equal to 4. So we don't know what x is, but our y value is 4. So there are two solutions here. We have one over here, which is at negative 2, and then another one at 2. So when f is at negative 2, our function is 4, and when f is at 2, our function is also 4. So in this next challenging problem, we have f at x is equal to 5 minus 3x, and we have g at x is equal to 4x plus 1. We want to find a value of x such that, so for this first question, we're looking for an x value where f at x is equal to g at x. Now we know what f at x is, and we know what g at x is. F at x is just 5 minus 3x, and g at x is just 4x plus 1. So we can solve this. These are just two linear functions, and when we have two functions that are equal to each other, we're looking for their point of intersection. So we can solve this by using substitution. So since we know f at x is 5 minus 3x, we're just going to replace f at x with 5 minus 3x. We bring down that equal sign, we replace g at x with 4x plus 1. Now we need to combine like terms, so we move all x's to one side and all constant numbers to the other side. So this is going to become 5 minus 1 equals to 4x minus 3x, plus 3x. So we have 4 equals to 7x, and that just becomes, if we divide by 7, x is equal to 4 over 7. The next question just requires a little more algebra. So we're looking to find an x value such that f at x plus 2 is equal to g at x minus 1. Now we need to input x plus 2 into our function f, and we need to input x minus 1 into our function g. So we know our function f at x is equal to 5 minus 3x. We need to replace this whole thing, x, with x plus 2. So f at x plus 2 is equal to 5 minus 3 times x plus 2, and we need to distribute that negative 3 into the brackets. So f at x plus 2 is equal to 5 minus 3x minus 6, and if we simplify that, that just becomes negative 1 minus 3x. Now if we substitute into our function g at x, so g at x is equal to 4x plus 1. We want to replace g at x, or x, with x minus 1. So that becomes 4 times x minus 1 plus 1. And again, we're going to distribute that 4 into those brackets. So it becomes 4x minus 4 plus 1. And when we combine like terms, g at x minus 1 is just equal to 4x minus 3. So we're not done. We're looking for the x value when f at x plus 2 is equal to g at x minus 1. Since we have a simplified expression for f at x plus 2, we can replace that with negative 1 minus 3x. And since we have a simplified expression for g at x minus 1, we can replace that with 4x minus 3. And again, since we're finding our x value, we're finding the x value where these two are equal. We can use substitution. So we want to combine like terms. That's going to become negative 1 plus 3 equals 4x plus 3x. And that just becomes negative or positive 2 equals to 7x. So if we divide by 7 on both sides, x is just equal to 2 over 7.